Let's take a look at Snell's law. Now, Snell's law deals with how light refracts or bends when it goes into water or any other clear substance. So it could be a clear soda, it could be glass or clear plastic like we use for eyeglass lenses. And it's a really straightforward formula. N1, which is the refractive index of the material you're starting out in, sine theta 1 equals N2 sine theta 2. And we'll see a picture of this in the next slide. Now, if N2, if the refractive index that the light is going into is bigger than N1, it bends towards the normal. And this will all become clear, like I said, when I show you the diagram. Now, if N2 is greater than N1, it'll bend away from the normal. So a place where we really see this, and you can see this in the image I have here, is when you have a straw in water. So if you have a straw in water, or like I said, in a clear soda like 7-Up or Sprite, you'll see that sometimes the straw looks like it's bent. And it's not really, or you could do the same thing with a spoon if you put a spoon into your drink. But it's just the way it looks. So if we look at air, air's refractive index is about 1. It's very, very close to what it is in a vacuum. Now, the normal is always perpendicular to the surface. Just like the normal force is always perpendicular to the surface if you're dragging a block when we learned about friction. Now, water's N is 1.33, so it's greater. So we see that the ray bent inward towards the normal a little bit. And Snell's law lets us actually calculate those numbers, and that's what we're going to do in a few minutes. Now, suppose this is glass. And let's say it has an N of about 1.5. That's roughly what glass is. It varies a little bit depending on the composition of the glass, but it's close enough for what we're doing. So the incident ray comes in at a certain angle, but notice N2 is less, so the ray bends outward. It gets refracted outward. Now, a place where we might see this is, we look at this example. So this fellow's waving to his friend who's in the water. As the light comes from water, which is N of about 1.33, it might vary a little bit because it's salt water, but it's pretty close to 1.33. Into air, 1.00. If we drew the normal, the ray bends. So what does this mean? For the person who's on the beach, that lady's foot is going to seem to be where her knee is. We're going to see that refraction. And we can see that picture with the soldiers here. I think they're Navy SEALs. And they look really, really short when they're in the water here. It's kind of comical. But they're not. These are normal-sized people. It's just the way the water is refracting. And with really thick glass, like you might see in an aquarium, like we could see this polar bear here at a zoo, there's a really, really thick glass. It has to be to support all that water. It actually looks like the poor polar bear is cut in half. He's not. He's absolutely fine. It's just a trick of the light. It's just refraction. So let's start to see some math with this, and it's always a good idea to draw a diagram. So we're going to shine a flashlight into a pool of water. So let's draw the surface of the water and draw the normal line. So when it comes into the water, it's going to come in at about 60 degrees. So this is from air, which is N equals 1. And you're going to see we're going to just keep drawing these kind of diagrams pretty much throughout the whole chapter. Now when it goes into water, N is 1.33. So what it's going to do is it's actually going to bend in a little bit. And we'll do some math to calculate that theta. Call that theta 2, N1 and N2, and then this will be theta 1. Now it's really easy. Snell's law isn't all that hard. So there's Snell's law. And we start to substitute. Luckily, we like it when it's air. I like it when it's air because then N1 is 1. Sine 60 degrees is 1.33. sine theta 2. Now, we could do all the algebra and take an inverse sine. I think for Snell's law, it's just easier to do it this way. Sine of 60 is just a number that we can punch into our calculator. It's 0.8660. 1.33 sine theta 2. So divide over the 1.33. Take an inverse or arc sine. And yeah, it did bend inward. It bent inward. Now it's only at 40.6 degrees. That's what we would see with the straw in the water. That's what we would see. Now, when we're looking at the lady in the ocean or the soldiers in the water, there we were looking at light coming up from their feet. So we're actually looking in the other direction. It works both ways. Now let's look at something different. Let's have light coming into glass and then exiting on the other side. So let's see. Light strikes the plane of glass at 60 degrees. So this would be our theta 1. And N1 is pretty close to exactly 1. Now they tell us the glass is 1.5. And that's pretty close to what pretty commonly it is in most glasses. So again, Snell's law. And we start substituting. We're going to see the math looks very similar because this is 60 degrees again. So 1 times sine of 60 is just the sine of 60, which is 0.8660. That's easy enough. Is 1.5 sine theta. Divide 1.5 on both sides, or divide both sides by 1.5, I should say. And we get a theta 2 of 35.3 degrees. Let me show you where that's at. That's right in here, if I shade it in. Now, if we use parallel angles, if we use these angles here, we would know that this theta is actually equal to this theta when it leaves the glass. I believe those are opposite interior angles in geometry if you use it, because those would be parallel lines. So it might be interesting to ask, well, what angle does it leave the glass at? Let's see. So in this case, it would be going from glass back out to the air. So we're going to have a theta here, theta in the glass, and we'll see what happens. And it should go out at a greater angle. So we just calculated that this angle is 35.3 degrees. But we're going to have to do the sine of that and then multiply it by 1.5. Oh, and then the other side is just sine theta 2. So 8.66. Oh, it works out to 8.66. Take the arc sine or the inverse sine. Hey, it exits at exactly the same angle that it went in at. But it shifted. If you remember from the picture before, when it came into the glass, it was over here. It actually got shifted a little bit. And sometimes you can actually see that when you look through glass or at certain angles, that things seem to be moved over a little bit than what they really are, especially for really, really thick glass like we saw with the polar bear. So the angle is the same, but the beam gets shifted over. Now let's do one where we actually calculate the refractive index. And this is a very common lab where we don't know the refractive index, or we do know the refractive index, but we want to double check it. So we might shine a beam of light with a little laser or a light source, maybe into water or into plastic. I've seen ones where they try soda and different sugar water. But let's see what we're going to do. So light is passing through water. So in this example, it's starting out in the water down here. And it bounces out at some theta 2. We can call this theta 1 down below, 56.4. And then it bends in towards the normal to some clear substance. It doesn't necessarily say that it's air. So it could be glass or it could be plastic, whatever we have this water stored in. So it's really important with Snell's law to remember which angles we're talking about. We're starting in the water. So that N1 is 1.33. We're starting at 56.4 degrees. Then N2, we don't know, but we do know the final angle because that's easy enough to measure. In fact, that's what we'll do in the lab. We'll use a protractor, and many other people will too. So 1.65. So that could be a type of glass. It could be a very thick plastic or something else. But we can use Snell's law to determine the index of refraction, and they do. Optometrists even need to know and people who make eyeglasses need to know the index of refraction of the different plastics that they make their lenses out of. Now let's try an unusual problem. Suppose a pool, let's say it's 1.67 meters deep, so that's maybe about 5 feet. Not unreasonable, 4 or 5 feet, not unreasonable for a swimming pool. And a pair of goggles is 100 centimeters from the side. So here's the goggles, when you throw goggles in the pool or you lose your goggles and you're trying to find them. So here's our goggles. And now 100 centimeters is 1 meter. Let's make it into meters. I like that a little bit better. Okay, so Mr. Seba stands 1.75 meters tall. We'll assume that's where his eyes are. And for once, I won't pick on him. I'll call him handsome. There we go. So let's see what has to happen. Here's the normal. Actually, let's move it over. So the light is going to come out of the pool here. We'll make the normal over here. Sorry about that. And it's going to bend. And in fact, it's going to bend outward because air is 1. So we'll call this N2. Now, why is it N2? Because the light has to leave and get bounced off the goggles. And then N1 is 1.33. And the pool is 1.67 meters deep. Now you might say, well, how are we going to go about this? We don't know this angle here yet. Right? We don't know theta 1. We can find it. We can find it. So what we're going to do is we're going to use some trigonometry here to get that angle. We're going to use opposite over adjacent. We're going to use tangent. Oh, and it looks like I did it in centimeters, but that's okay. So we can get that theta 1 as 30.9 degrees. Great. Now using Snell's law, we can get theta 2. That'll be the angle that it leaves the pool once it enters the air. So remember, we were starting out underwater. N1 is 1.33, and we just calculated that angle using trigonometry. Well, we could put sine of 30.9 in our calculators, multiply it by 1.33. We get theta 2 is 43.1 degrees. Now let's assess where we are and what we know. Mr. Seba is 1.75 meters tall. There's Mr. Seba. We want to know this distance. Give him some arms. And we know this angle is 43.1 degrees. Well, this has to be a right angle. So we can use 90 minus 43.1 degrees to get that inside angle, which is 46.9 degrees. That's in here. Sorry if it's a little small. Then we'll go back and use tangent again. Now you might ask, could we use a different trig function? Sure, you could. But you'd have to find that hypotenuse first, and it would just be messy. Tangent's actually the quickest way to do it. So the opposite is 1.75 meters, and the adjacent is x. So from this point out, it's just a little tiny bit of trigonometry, a little bit of algebra, plug it into your calculator. And it turns out that if he stands 1.64 meters, he'll be able to see the goggles. Now you say, what if he steps further back? He won't be able to see them. He won't be able to see them at all. Now, if he gets closer, he'll still be able to see them. But if he moves further away from the pool, back to where his deck chair is or his patio, he wouldn't be able to see them.